All right. Why don't we get started? So, reading, please make sure that you are keeping up with the reading. We do have exam number 2 on Tuesday, and we'll cover issues about interprocess communication, just a little bit about general processes, and some on threads. Certainly, it is not cumulative, but material from operating systems does kind of fold in on itself. And so it will be the scoped in one class meeting. It'll be similar types of questions, but fewer since the actual number of different topics, since it's not overview material, will be less. And again, like last time, you'll be allowed one 8.5 by 11 sheet of paper for your notes, both sides. Okay. Any questions about this or the threading example, threading lab? No. All right. So where we left off, we talked about this idea of priority scheduling. And in priority scheduling, we have a number, an integer. It could be real valued, but typically it's an integer. And this integer connotes the priority. That is, the smaller this integer, the higher the priority, or the larger the integer, the smaller the priority, or lower the priority. And so essentially what the scheme does is it is a key, as it were, that's used by the short-term scheduler to take processes or select a process off the ready queue and give it to the CPU for execution. And so this idea of priority-based scheduling has some issues associated with it in that because the selection criteria is based on this notion of the highest priority, i.e. the lowest priority number, that means that if you have two processes, P1 and P2, and let's assume for the sake of consideration that P1 has a higher priority, so its priority number is like say 5, and let's say P2, its priority number is say 10. Right? So that means if they're both sitting in the ready queue, the scheduler will always select priority process P1 over process P2 because it has a higher priority. And so one of the issues that can happen with priority scheduling that you will see is this idea of starvation, meaning that one of the processes, because it's lower priority, might come to the scenario where it is not making progress until the other processes have completed in their entirety. And so there are two versions of priority scheduling. One is called preemptive and the other is non-preemptive. With the non-preemptive version of priority scheduling, once that particular thread has used up its time on the CPU, it exits and then the next higher priority one is selected. With preemptive, that means that the moment a higher priority process arrives, whichever process or thread has the CPU is kicked off and it's given to that higher priority one. And so this non-preemptive versus preemptive says, can you be interrupted if somebody during your execution, can you be interrupted if some other thread comes along that's associated with a higher priority? Okay. Any questions about this? Does that make sense? All right. So that's where we left off, and continuing on from that. So this problem of starvation, of course, there is a solution to it, and the solution is called aging. And there are different ways of implementing this aging. And essentially, what aging says is that the longer a process or thread is in the system, even if it starts as a higher priority, the idea is that it's making progress because it's gotten some time from the CPU. And so every time it uses the CPU, its priority is increased, so it starts to become lower and lower and lower priority over time. And in this regard, now, processes that have entered the ready queue and that are associated with lower priorities, i.e. higher priority numbers, they're going to have an opportunity to get the CPU because eventually this long-lived process is going to have its priority drop so low that it's going to be a lower priority than that original process that was a lower priority at the outset. And so this aging is a solution for getting around this issue of starvation because at the end of the day, if you have a system, this idea of having priorities is to allow a preference for a certain process, and that might be because it's a critical operation for the system, or maybe you have a so-called real-time system. And in a real-time system, those computations are different in that you're not just concerned about what the process or thread is doing. You're also concerned about when it completes what it's supposed to be doing. And so real-time systems is an entire field unto itself, and you could get a graduate degree focusing in real-time issues in operating systems. I hope you do. Real-time systems are typically tied to embedded systems, and they deal with equipment or machines and things like that that interact with the real world. Because if you think about it, let's say you're flying in an airplane, right? And most jumbo jets and even small aircraft are digital, right? And so let's say you have the control surfaces and you pull back on the yoke and you want to give the rudder a little bit of change, right? Well, between the time when you pull on the yoke, especially if it's drive-by-wire, and the time when the rudder actually responds or the elevators respond, the control surfaces on the aircraft, you need that to happen in a specific amount of time. And so how you design operating systems for which some tasks require a timeliness, they have a hard deadline associated. When I execute this, it must finish within a certain fixed amount of time. And typically that's measured in milliseconds. Um, those real-time processes require a lot more time from the CPU, and oftentimes in some system, how they allow you to have different types of tasks, both real-time or, or non-real-time, so-called best effort tasks. They often use the priority system as a means of implementing that. Now, in a full-blown real-time system, you do something called rate monotonic analysis. You have your tasks, you time them, and then you lay out a schedule that's very specific to the amount of time that each one of these tasks take to complete for each iteration of these tasks. And these tasks are typically iterative, right? You do something and then you do something again. If you think about a sensor application like radar, right? You take a radar return, you compute a distance, and then you report it. Then you take the radar return, you compute a distance and report it. And so oftentimes these hard real-time tasks are expressed as something that happens again and again and again iteratively. Okay. Any questions about this? All right, so aging is a way of getting past this issue of starvation in a general purpose operating system, and it's essentially a way of ratcheting back the priority of a process to give other processes an opportunity to gain preference by the short-term scheduler to get picked off the ready queue for execution. Okay, so here's an example of priority scheduling. And on the left-hand column, your left, we have 5 processes, P1 through P5. And then we have their respective burst times, 10 milliseconds, 1, 2, 1, and 5. And then we have their priorities. And again, remember that the smaller the priority number, the higher the priority. Right? You can almost imagine a priority as saying, what spot do you occupy in line if you have more than one item sitting, more than one process sitting in the ready queue. And so the priorities for P1 is 3, for P2 it's 1, for P3 it's 4, for P4 it's 5, and for P5 it's 2. So let's assume at some time T0, all of these processes arrive in the ready queue, regardless of where they might have come from. It could be that they were formerly waiting on some I/O device in a wait queue associated with that I/O controller, or it could be that these processes were new processes admitted to the system. Somebody ran a program. And so regardless, let's assume that at some initial time, 0, all 5 of these processes, P1 through P5, arrived in the system. And so because P2 has the highest priority, the short-term scheduler is going to select P2 for execution. It does so, and P2's burst time is 1, so at time 1 millisecond, P2 completes. So next, it looks for the next highest priority, that would be P5 with a burst time of 5. So from 1 through 6, P5 executes. P5 is selected next, and it finishes at time 6. Then after that, of course, P1 is selected. Its priority is 3. It's the next highest priority. Its burst time is 10, so it completes at time 16. Then we follow that with P3 for burst time of 2, and P4 finally with a burst time of 1. And so again, here in this case, because the assumption is they all arrive at some initial time T0, each one waits a certain amount of time. So P5 waits 1 millisecond before it executes. P1 waits 6 milliseconds. P3 starts with a wait time of 16, and then lastly P4 waits 18 units or 18 milliseconds. And so if you take the average of all of these, the average wait time is 8.2 milliseconds. Okay. Any questions about this? Does that make sense? So this particular example is just a simple one of priority scheduling, and the idea is to associate this priority a number with each process, and the short-term scheduler uses this priority as a criterion for selection of the next process or thread that's going to execute on the CPU. Okay. So another type of scheduling, which maybe I don't know, no, maybe not, I don't know, that people are very kind of naturally familiar with or makes a lot of sense is so-called round robin scheduling. Now, in round robin scheduling, each process or thread gets a standard unit of time, delta t, it's called a quantum, and each process that's waiting in the ready queue gets a single quantum from the CPU to execute, and then is put back onto the ready queue at the back. And so you can imagine you have these processes waiting for the CPU lined up in some order. It doesn't matter what the order is. And the scheduler, short-term scheduler, goes to each process in line in kind and gives each one the same amount queue worth of time on the CPU. Right? And so it's called round robin because if you imagine a bunch of processes waiting in the queue, the first one gets queue amount of time, then the second one, then the third one, then the fourth one, fifth one, and so forth. And each time someone gets some amount of time, now they go to the back of the line, and eventually they get to the front of the line again and get that delta t or that quantum of time on the CPU. So essentially, what this round robin implements is the equal sharing of the CPU among a set of processes or threads that are sitting in the ready queue. And so if you imagine some span of time, and you might imagine it's an hour or 10 minutes or what have you, because it's giving an equal amount of time q, a quantum, to each of the processes waiting, in the limit, each one gets an equal share, 1 over n, for n waiting processes, gets an equal share of the CPU. Okay? Any questions about this? Make sense? Yeah, okay. So this is an example, and of course, if you have n processes or threads waiting in the ready queue, you get 1 unit of time q, and then it takes all the other n minus 1 processes that are waiting to get their equal share q of time on the CPU before you get another q amount of time again. And so that means that you're going to get q amount of time as a process, and then you're going to wait a time n minus 1 times q before you get your next round on the CPU. Now, certainly if n grows or shrinks, it adjusts appropriately with this fair sharing, as it were, of the CPU's time. Okay, so there are the mechanism by which this works is using a timer, and that timer essentially acts like a stopwatch and measures 1 quantum of time, regardless of what that length of the quantum is. And when the timer expires, it fires an interrupt, and that interrupt is used by the short-term scheduler and the dispatcher to do that context switch. And so there's some performance issues associated with your quantum, and in fact, in many or some operating systems, you can actually change the quantum of time, and that dramatically affects the performance characteristic of your system. And for server operating systems, tuning such things is very typical. They often expose in server versions of operating systems, they often expose the controls for tinkering with things like the page size, the quantum size, and all sorts of other things. And so if your quantum is very large, and it's large enough to satisfy the burst time of all of your waiting processes in the ready queue, then it acts like FIFO scheduling, meaning the order in which they arrive is the order in which they're executed. Now, of course, if your quantum is small, each of these waiting processes in the ready queue gets an equal share of the CPU, which is all fine and good, but you can't just make your quantum size arbitrarily small, because if it's too small, you get some really bad things that happen. And recall what happens with the dispatcher. The dispatcher is that part of the kernel that is responsible for physically implementing or carrying out the work of the context switch. It's responsible for storing all of the currently executing processes information into a PCB, process control block, and then loading the CPU with information for the new process that's going to take the CPU or run on the CPU. And so if this dispatcher takes some amount of time that is too close to Q, or let's say Q is smaller than the amount of time that the dispatcher needs in order to context switch, you're going to have a lot of problems. And so essentially Q, however small you want to set it to implement this fair sharing of the CPU, you have to make sure that it's at least large enough or sufficiently much larger than the dispatch time that it takes to actually do the context switch. Because if it's too small, let's say it's only just big enough to do the context switch, that means all of that time Q, you don't want to spend all of that time Q just doing the context switch, and the process never really gets a chance to run, right? And so you can set Q as large as you want. You can, with a caveat, set it as small as you want, but it can never be so small that it's the same amount of time as the dispatch, the overhead that it takes to physically copy from the PCB to the CPU and the CPU back to the PCB when you're changing context. Okay? All right. Any questions about this? Does that make sense? Bless you. So let's take a look at round robin, and let's make the assumption and this is in the book, that the quantum is 4 milliseconds long. And we have three processes that come in order into the system in the ready queue at some time t0. We have process P1 with a burst time of 24 milliseconds. Process P2 has a burst time of 3, and process P3 has a burst time of 3. Now, certainly, if the burst time is smaller than the quantum, that means the process is finished. Maybe it's going from a CPU burst switching to an I/O burst. It's going to jump off the processor, right? And go into the wait queue for that respective I/O controller. And so once the burst time is done, if the quantum still has some time left over, it's now going to switch to some other process. Because it's not going to set, the CPU is not going to set I/O. So here we have P1, P2, and P3. And so P1 comes in first, and it gets 1 quantum, 4 units. So P1 executes for 4 milliseconds. And then P2, which is next in the queue, it gets 4 milliseconds. Now, when P1's initial burst of 4 milliseconds corresponding to the quantum, when that expires, P1 is kicked off the processor and rejoins the ready queue. So then P2, which was second in the queue, it gets selected by the short-term scheduler, and it receives 4 units of time, 4 milliseconds, which is the quantum, to execute on the CPU. But P2 only uses 3 of them, so after P2's execution, it ends at time 7 milliseconds. P2 is done, and it comes off the CPU. So then after that, P3 is next, and so we run P3 for 4 milliseconds worth of time. And here we see from the chart the burst time of P3 is only 3 milliseconds. So P3 executes and then is kicked off the CPU. It's done. And so you'll notice here with this round robin, we start with the first process, the second, and the third. Each one receives 4 units of time until they complete. So we start out, we say P1 executes, P2 and P3, and at that juncture, at time 10, P2 and P3 are done with their burst. So they're they're not going to be rescheduled. They're done. So then after that, all we have as an active process in the ready queue is P1. So P1 gets 4 units of time, okay? And then P1 gets 4 more units of time. And then P1 gets 4 more units of time. And that continues because it's the only thing in the queue until P1 is done with its burst. Okay. Any questions about this? So certainly, let's say after P1 has finished at time 18, if some new process, say P4 came along, then P4 would get some time instead of P1 getting all that remainder of the time. And so this round robin cycles through the FIFO queue and executes each process in that FIFO ready queue in kind, but giving each one some unit of time queue as set by the quantum, and then it cycles through, giving each one some amount of time. Okay. All right. So I alluded to that before, that the quantum should be bigger than the dispatch time, or else you're going to have some serious problems. Okay. Any questions about this? Make sense? All right. So let's take a look at context switch as it pertains to processing time. So if you set your quantum suitably, you're not going to incur as many context switches, right? Because the more time means the fewer periods when it's going to kick someone off the processor. And so tuning the quantum size is very important, especially to high performance applications. You don't want to spend a lot of time doing context switching, and this is really illustrated well by this figure, and this is something from the book. So let's say we have a span of time, and that context switch, it doesn't take zero time. It takes roughly about 10 milliseconds physically to perform the context switch. So if there are certain applications that you want to run fast, yes, you want to set your quantum small enough so that you give each process the ability to make progress. You want to increase your degree of multi-programming, but you don't want to set it so small that you're spending a lot of time cumulatively performing the context switch. Because when you're performing a context switch, you're not actually performing work as defined by the program or the process. So you want to strike the right balance. Now, how does that happen in practice? Well, you load up your server instance, you set some performance tuning parameters like the quantum and other things, and then you run your applications and you instrument your system and actually measure the result on performance for these choices. And then, of course, you try a number of different choices and you see which one leads to the right performance for your application. And so, if performance to you means that you can have a larger number of concurrent connections, say you're, an e-commerce server and you want to make sure that more people can buy at the same time. Right, you're getting ready for Black Friday or what have you, and you want to make sure that your system scales. Now, in that case, you're going to prefer quantum sizes that lend themselves well to scalability on a server. Or maybe, you're a media streaming organization and you want to make sure that the media stream throughput end to end is maximized, right? Because the more video data that someone gets per unit time, the better the experience for media streaming. Now, certainly, you'd get a bunch of servers, set these performance tuning parameters like the quantum size, and you measure the impact of that on the amount of bits per second that you can get from the server endpoint to the client endpoint. So performance tuning, it's part science, part art, but setting the quantum size appropriately will have an impact on the number of context switches, and the number of context switches takes from the amount of actual work your CPU can do, because when you're context switching, no other work happens, right? That's the copying of information from the CPU to the process control block, and then taking the PCB for the new process and copying that onto the CPU. So no actual work happens. So in this case, and this is in the book, we have a process time of total of 10 units of time, or 10 milliseconds. And let's say we set our quantum to 12 milliseconds. Now, in that case, over the course of the 10 milliseconds of processing, this is just pure execution on the CPU. Okay, great. And we have zero context switches. So that means over this whole 10 milliseconds of time, we're not spending any proportion of that on the context switch. Now, the context switch is only about 10 milliseconds that it takes, but you can imagine if you decrease the quantum, then over this span of time, you're going to spend multiples of 10 milliseconds where you're not doing any work on the CPU. So let's take this next example, and let's say the quantum size is cut in half to be 6 milliseconds. Now, over this span of 10 milliseconds of time, so you can imagine, you set your stopwatch at 0, and then 10 milliseconds later, you stop the stopwatch. Now, in that case, right at the 6 millisecond point, that quantum expires. And when that quantum expires, that marks one context switch, and that's when the dispatcher actually does that shuffling of information between the CPU and the process control blocks in implementing that context switch. So during that time, that one context switch, no work gets done. And once the context switch is done, well, another 6 milliseconds worth of quantum is used to measure this process. And so this particular 10 milliseconds of processing time, if we have a quantum size of 6, milliseconds, we're going to incur the overhead of one context switch. So we're going to have 1 times 10 milliseconds worth of time during this 10 milliseconds where we're not doing any work. Okay? All right, so likewise, let's say we kind of go to an extreme here and we set the quantum size only to 1 unit, right? So that means every 1 millisecond, we're going to context switch. So over this processing time of 10, we're going to do this context switch, so the dispatcher's work is going to happen 10 for 9 times during this period. Now, of course, if your context switch took 10 milliseconds, you're going to use up the entire 10 milliseconds just on doing dispatcher work, meaning like no work would happen. And so what this really illustrates, now this is a dramatic extreme on the bottom, right? You'd never have this in practice, but the point is taken in the illustration that the more context switches you have, the smaller the percentage of the effective time here, the 10 milliseconds, the smaller percentage of that you have to actually do real work, where real work is the actual task encoded by the code for that process. Okay? All right, question, yes. Mhm. Ah, it's 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 it is a limiting factor, and so in this particular case, in the extreme, and you'd never really do this in practice. This is just to illustrate something. But yes, it is a limiter because for every context switch, so if you have a bunch of processes happening, and let's say, you have kernel threads implemented on your machine, and let's say you have a database that's doing some, indexing and lookup for something on disk, and let's say you also have some other threads interacting with the network card, taking incoming requests. And so at the end of the day, if you're implementing, say, that's an e-commerce or video streaming, you want the video stream to come off the disk quickly, right? So you certainly want that thread that's interacting with the storage database or the file system. You want that to make progress, to have time on the processor. And then also, you don't get the incoming movie request to stream video if you're not interacting with the network card. So you want that thing to make progress. And so there's a tendency to say, okay, well, if I want more parts of my application, more tasks within my application to make progress, I want to kind of make sure that I'm sharing the CPU more evenly or more frequently. But if you're too fair, so to speak, then the cost of that fairness is in the cumulative amount of time when no work happens when you're doing the switching. And so to answer your question, I just kind of set that context first. To answer your question, that is a kind of limiting factor that you want to make sure the quantum uh, more than pays for the amount of time that you spend where you're doing nothing because the dispatcher is physically performing the switch. So certainly you would never have the quantum directly equal to the dispatch time. You'd have it bigger. How much bigger? It depends on your application. Certainly, you want to have it big enough where maybe it's like 90% bigger, or the dispatch time is only 10% of the quantum. Where you're kind of not doing any work. But that also depends on the application. There's no one prescription for how to do that, especially when you have things like network card and file system, because those also introduce weights with their associated I/O controllers and the weight queue. So it is a little bit science. The science part is knowing what parts of the system do what, but the art part is when they interact with one another. So you're adding in the weight queue plus the dispatch overhead plus the quantum size. It's sort of this balancing of things together. That is the art part of this. Did I answer your question? Yeah, okay. Any other questions? Great question. Um, any other questions? No? Okay. So certainly you want to make sure that the quantum size more than pays for the dispatch time so that it's so much bigger than the amount of time it's spending doing nothing that it's not as noticeable. Okay. So this is just an example, and this is in the book, and it's a graph that compares the size of the quantum to the turnaround time, the time for which the process runs, and it returns something back to the user of this process. And this is average turnaround time, so it's in aggregate based on these set of processes, and these processes have turnaround times individually of 6, 3, 1, and 7. And so they talk about the CPU bursts as being, 80% of the bursts should be shorter than the quantum, right? And that means you should have a quantum size, and this is their recommendation from this example. But if you change the application, of course, everything depends on what you're trying to do. But in this case, what that says is that your quantum should be bigger than 80% of your CPU bursts. And what that means is 80% of your processes can complete a single burst, whether it's a CPU burst or an I/O burst, in one quantum of time. Right now, depending on your application, you might change that, especially if your profile, i.e., the number of processes that are I/O bound versus the number of processes that are CPU bound, if that balance changes dramatically, this is going to change. But that would require you to fully spec out what you want each server instance to do and look at the performance profile and do some extensive benchmarking. So here on the horizontal axis, we have the time quantum in milliseconds, and then we have the average turnaround time on the vertical axis. And what you'll see, of course, certainly in the beginning, as you start out with a quantum of size 1, okay, you have a baseline. And as you increase it, you'll notice the turnaround time starts to increase. Now that might seem counterintuitive because, I thought you said if the quantum increases, it's more likely that a process will complete sooner. But at this juncture, when the quantum is pretty small, in the beginning, when you increase it, that leads to a process having to wait longer, right? So the turnaround time is longer if the average wait time is longer. But then what happens once you increase the quantum to a certain point? In this case, when we go from a quantum of size 2 to size 3, we see the turnaround time start to drop. And you'll notice here, when we go to a quantum of size 1, the only process that can finish its burst cycle with a quantum size 1 is P3, right? And then we increase it to 2. Well, P3 is still the only one that can complete a burst cycle in one quantum. And then once we go to, but also when we go to 2, no other processes complete, so we're going to do an additional context switch, but that means they also wait twice as long, going from one quantum to a quantum of 1 to a quantum of 2. So then once we increase the quantum size to 3, all of a sudden, process 3 can complete in one quantum, but process 2 can also complete in one quantum. Moreover, for process P1, right, it's a size 6, so process P1 certainly is going to get 3 quantums worth of time if it's a quantum of 2, but it's only going to need 2 of them if it's a quantum of size 3. So in aggregate, what that means as we go from a quantum size of 2 to 3, more of the processes complete in that time. Moreover, we have fewer context switches needed for each of these processes, and the result of that is the average turnaround time you see drops from 11.5 to 11 when we go from a quantum of size 2 to 3. And so that's just an illustration of the impact that the quantum size can have. And then all of a sudden, we go from 3 to 4 and things start to increase. Now, when we go from 3 to 4, well, already when we're at 3, we know P3 and P2 can complete in one quantum, and we know that P1 needs 2 quantums worth of time. But when we go from 3 to 4, that does not affect the amount of quantums needed by P1 and P4. They both need 2 quantums, right? Because 2 times 4 is 6, that will cover the 6, and then 2 times 4 is 8, that'll cover the 7. But the problem is, in increasing this quantum, we're also increasing the wait time of those that aren't executing during that quantum of size 4. So that has the impact of increasing the average turnaround time because those that are waiting, they're waiting longer now because the quantum size is 4. So then we go to quantum size of 5. Okay, things continue to increase for the same reason. But once we go to a quantum size of 6, we'll notice the average turnaround time decreases. And the reason for that decrease is, of course, now in one quantum, P1 can execute in its entirety. Okay? All right. So any questions about this? Please get familiar with why this graph looks the way it does. And that's an important task. There's a lot of work out there for people who are server engineers and data center engineers out there. And you do things like this performance tuning day in and day out, among other things concerning network topology. So if you're interested in cloud operations, server engineering, things like that, in data center, this sort of thing should be very important to you, or would. All right. Any questions about this? All right. Make sense? Yeah. Okay. So let's continue on. Another way of balancing between different priority level processes is this so-called multi-level queue. And essentially what you do, instead of having one ready queue, you have more than one ready queue. And each ready queue is associated with different ways of scheduling or different prioritizations. And in doing so, you can also prevent that issue that we called aging, but also balance your performance characteristics of your system because the dispatcher and the schedulers are selecting from different queues for different purposes. And so one way of partitioning the ready queue into separate queues is to have a so-called foreground queue, which is for interactive type processes, things like your keyboard, your graphics, and things like that. And the other queue is a so-called batch queue. And so in this sort of partitioning, this multi-level queue approach, the ready queue is separated into two different ready queues, and different scheduling disciplines are used for the foreground queue. In this case, it's round robin. So each process in the foreground queue is given an equal share encoded as a quantum of time for the processor. And then the background queue, it's first come, first serve. And this background queue is for batch operations. These are things like your, Dropbox daemon, right? It wakes up, it does something without necessarily interacting with the user, and then it is done, right? Completes. Now, recall with round robin, it tries to increase the degree of multi-programming by fair sharing equal portions of the time of the CPU among a bunch of processes or threads. Now, this fair sharing means that each process makes progress. And if you think about what happens in a graphical system, right, you want your keyboard to continue to interact. You want things to look responsive, like it's paying attention to what you're doing, and you also want your graphics to update frequently. So if you have all of these tasks happening and you want them to be responsive to you, then this round robin scheduling is a good thing to do because it gives you this responsiveness since all of your processes are making progress. Okay. But with your batch processes, things like interacting with your file system, well, they arrive in the ready queue because there's something to do. So this first come, first serve scheduling discipline makes sense for things like your Dropbox process. Okay. Likewise for email. Is there incoming email? Yes. Then you go ahead, you take that data from the network card's I/O buffer, and then you put it in some mailbox, for example, on your machine. So each queue, the foreground and background, has its own scheduling algorithm. The foreground has a round robin scheduling algorithm for fair sharing of the processor, and then the background has first come, first serve scheduling discipline. Okay. Any questions about this? So scheduling must be done between the queues. And so there are many ways that you can have the scheduler interact with this foreground queue and this background queue. You could have a prioritization scheme. So perhaps, maybe if there is anything in the foreground queue, then you're going to prefer those processes. Question? Um, if you have anything in this foreground queue, you're going to prefer, the scheduler is going to prefer that. So if there's any process waiting for service in the foreground queue, then it's going to pick that before it picks anything in this background queue. You could also slice up time and do something like, okay, well, 80% of the time, the scheduler is going to pick something from the foreground queue, and the remaining 20% of the time, it's going to pick a process from the background queue. Either way works, and it's a way of giving a scheduling profile, if you will, to processes that need it, and then you partition these processes based on the type of work that they do. You send them to a different ready queue. And so in this particular example, foreground queue are anything, any processes that interact with the user, like graphics and keyboard, and the background queue are those things that don't interact with the user. Okay. Any questions about this? So one way of balancing the workload of your system to get efficiency is to take your ready queue and to break it into pieces, so-called multi-level queue, and you can then associate different scheduling approaches to benefit certain types of tasks. Okay. So Here's an example of multi-queue scheduling. And in this case, in this example, you have 5 different scheduling queues, and each one has a different priority. Now, when you implement these prioritizations associated with different partitions of the ready queue, this can be achieved by percentages, i.e. giving 80% of the scheduler's time to one queue, and then another 5% to another queue, and 1% to another queue, based on time partitioning. Or it could actually be a prioritization to say, all right, priority 1, the highest priority is one queue, priority 2 is another. But with that, you're going to have to deal with the issue of starvation, right? So there are different ways of partitioning it, and in this particular example, it illustrates, and this is in the book, it illustrates why someone would want to have multi-level queuing. And so in that case, the highest priority queue you'd reserve for system processes, because the system has to do its maintenance. It implements system calls in the kernel. Maybe there are things about bookkeeping with memory. Maybe it's the I/O subsystem for interacting with the disk drive and so forth. And so there are certain processes that are ultimately highest priority that you want to always get preference, because the system maintenance and system operation has to happen. And so in that case, you can have the highest priority partition of your ready queue be devoted to these system processes. And then next, you might have interactive processes. Now, interactive processes are things that you see as a user, like your graphics, right? A button depresses, and that button goes from the undepressed state to a different drawing of that button that looks like it's pressed in, right? Those are interactive processes. And then maybe your next priority would be things that you use for the editor. Now, when you're within the editor, right, and you're typing a document, it's kind of nice to see that character get rendered or drawn on the screen the moment that you press the keyboard. And so if you think about that, things that are interactive editing processes, you want to have a pretty good fair sharing, because you want it to be as responsive as possible. And then after that, you have batch processes, and then maybe some low-level processes you submit when you want an extra CPU. They call it student processes. Okay. Any questions about this? Make sense? So in that case, you can have more than just 2 multi-level queues. You can have 5 or even more, or you could have less, and you associate a priority with each one, whether it's temporal or fixed priority, and that way you can devote certain types of priorities with certain types of functions on your system. So this idea of partitioning your workload means separating out certain types of tasks as expressed by the scheduler based on how important you think they are to the system's operation. Okay. Any questions? No, everyone's pretty quiet. So this issue of aging can happen when you have these multi-level priority queues. And aging, rather not aging, starvation. So take, for example, you have a system process. Let's say someone wants to use the editing process. They're typing something in a word processor, and they need some time, or their process needs some time from the CPU. And then all of a sudden, a system process comes along, a system call is executed, or the kernel is dispatching something, or some other bookkeeping is happening with the file system. Now, of course, if you have a fixed prioritization scheme, right? Your editor, you're trying to type and you want to see that character you type drawn on the screen, but then a new system process comes along, and then another system process comes along. What ends up happening to you is that here you typed some character on the keyboard, and it takes a long time for you to even see that character being drawn on the screen. That's kind of weird if you're using a word processor. And so this idea of starvation is very real when you have these multi-level queues. And so the aging process can be implemented using this notion of feedback among these multi-level queues. And what this feedback among multi-level queues does is it says, okay, well, I know I have one queue in the multi-level queue that is associated with a higher priority. Once some task has been scheduled to execute associated with that particular high priority ready queue, then I'm going to demote it to join a lower priority ready queue. In that particular case, then things that start out as high priority, as they continue to get the CPU again and again and again, they end up dropping in priority down to the lowest priority, and the effect of that is aging. And this, in essence, the longer a particular process runs, the lower and lower it gets in priority, and therefore lower priority tasks eventually get a chance to execute. Okay, they're not starved out by high priority. Okay. So let's take a look at these queues. And in fact, with this multi-level feedback queue, you can have entirely different scheduling approaches for each of these queues, right? So in this particular example, we have three queues: Q0 at the top, Q1 in the middle, and Q2 at the bottom. In Q0, the quantum is 8, and then Q1, quantum is 16, and then it's first come, first serve in that third and final queue at the bottom. And the scheduling approach in Q0, that top queue, it's a quantum of 8, but it uses round robin, right? So that's that fair sharing, and round robin increases responsiveness because each process gets an equal share of the CPU. Q1 is also round robin, but it's round robin with an increased quantum size. And we saw before, when the quantum is smaller, you incur an increased overhead because all of that dispatch time is increased because you're context switching more. But you have increased responsiveness. If the quantum is larger, as is the case in Q1 in the middle there, that means you are more likely to complete the burst cycle for that process. So that means things are waiting less time, even if you're not fair sharing as well as the case where you had a smaller quantum. So in this case, Q1 says, I want to complete the burst time because the quantum is bigger, whereas Q0 says, I want to do fair sharing because I really want responsiveness. So then at the end, Q2 does first come, first serve. So it says, I will give you time on the CPU in the order that you get there. If it's not responsive and the burst time hasn't completed from the Q1, then go ahead and run it in the order that it arrived. Okay. Any questions about this? And so in this diagram, you'll see an edge that goes into each one of the queues, right? That's the ready queue. That's the place where new tasks are added to the respective multi-level ready queues. And then if they complete, then they're gone. And that's the edge that's outbound from each one. Otherwise, if they're not yet complete in their execution or their burst, they get demoted to the queue below. Okay? All right. Any questions about this? So this is an approach for implementing aging. Aging can happen by bumping down the priority, but in the case of the multi-level priority queue, aging occurs by migrating your task or your PCB, as it were, to a different queue in this hierarchy. Okay. Any questions about this? All right. So a new job enters Q0 and it's served or gets the CPU round robin. It executes for 8 milliseconds, and that 8 milliseconds, part of it is the dispatch, right? It's carved out of the dispatch. If it doesn't finish in the 8 milliseconds, it's moved to Q1. Again, in Q1, once it uses round robin, it's selected, it gets 16 milliseconds. Carved out of those 16 milliseconds is the dispatch time. If it still doesn't compute, it's preempted because that quantum expires, the timer fires, and it's interrupted and kicked off the CPU. So it goes to Q2, and then it executes first come, first serve. Okay. So let's take a look briefly at thread scheduling. And thread scheduling is particularly interesting if you have more than one CPU or more than one core on your system. So the distinction here is between user level threads and kernel level threads. A kernel level thread is actually seen by the system, meaning that it's scheduled on a CPU, right? Regardless of if that CPU implements threads in hardware, hardware threading, and most modern processors do these days, or if it's not hardware threading. So we talked about these thread models as being the relationship between the number of user level threads and the number of kernel level threads. It can be many to one, right? So that means one kernel thread is responsible for giving CPU execution to multiple user level threads, or we could have many to many, which is done through a construct we call lightweight processes. And so essentially with lightweight processes, we have some number of kernel threads. And so these kernel threads are seen by the operating system and seen by the CPUs, meaning they know they exist and the units of execution at the chip level. And these kernel level threads are associated with user level threads through some threading library. And so here we have this thing called process contention scope. And essentially, with this process contention scope, you can imagine a scheduler implemented at the user level in software. And what this software does, it says, okay, I have so many cycles, if as it were, or some amount of time from the kernel thread to which user level thread am I going to give my cycle, right? And so you can almost imagine a kind of software ready queue implemented in some library and user level space. And this ready queue has these user level threads, and they're given some piece of time or some unit of time by the kernel level thread, right? So this is called process contention scope because the competition as to which user level thread is going to be selected is done within the process in the user level space. And this is often done using a prioritization scheme. And this prioritization scheme literally allows you to set some integer that associates the preference for each one of these user level threads in being selected for execution by the kernel level thread. Okay, I thought that door was locked. That's actually always weird when you see someone pop their head in. Okay, likewise, because the kernel level threads are available on the CPU, they're seen by the CPU. In the literature, you'll see something called system contention scope. Now, system contention scope refers to the fact that when you're trying to make a decision as to which kernel level thread is going to get the CPU, it's among all kernel level threads when they compete. And by competition, what that refers to is that they're all in a ready queue, and the short-term scheduler is making a decision as to which of these kernel level threads is going to get the physical CPU. Right? So that's called system contention scope. So there's an API in Pthreads that allows you to set your process contention scope or system contention scope, and it's using the Pthread set of APIs, and I won't really cover this too much. But if you're programming in C and you're using Pthread, you can actually set and play with these control parameters to influence the performance characteristics of your system. And so the first thing you would do is you would get the contention scope for your thread, and then you would go ahead, call another API call to set the contention scope before you actually dispatch this thread so that it's now being considered by a scheduler, be it the user level threading system or the kernel level threading system. So in this example here, we include pthread.h, so that's the threading library for pthreads. And it doesn't matter how many threads there are in this particular example, it's 5 threads. And so here we do a pthread attribute init, right, in C. And then here we're doing a get scope, a pthread attribute get scope. And what that pthread attribute get scope is doing is saying, okay, well, all the attributes on my thread in the POSIX threading system, I want to retrieve whether it's a process scope thread or a system scope thread. Now, if it's a system scope thread, that means this particular thread is a kernel thread or is backed by a kernel thread, and therefore any sort of changes you make, whether it's priority or affinity and other things like that, is going to affect the scheduler as seen by the CPU. Right? If you find that it is a process scoped thread, that means it's only going to be impacted, those choices you make are really only going to impact the threading system in your user level process, i.e. the threading library at the user level, and it's not going to be seen at the kernel level by the CPU. Okay? All right, so here we retrieve what the scope is, and then in this next line, you'll see this pthread adder set scope. That's where you actually set the scope of it. Now, of course, what can you do with this? Well, let's say you create some threads in a threading library, and you have this many-to-many approach for doing your threading. Now you can decide, is this thread going to be one-for-one mapped with a kernel thread, or is it just going to get part of a kernel thread's time as part of a set of user level threads? Does that make sense? And so you can decide programmatically which one of the threads in your program, and that boils down to which one of the tasks you execute, are going to be influenced directly by kernel level thread scheduling decisions. Okay? All right, so why would you want to do that? Well, you might want to do that for performance reasons. If your threading is seen by the kernel, then things that are highly based on I/O are going to be impacted, right? You might also, if you have a process or a set of tasks that are compute bound, well, you don't want to pay the cost necessarily of thread dispatch every time you want to switch from one CPU bound calculation to another, right? So if you have each one of those CPU bound calculations as a user level thread, you give them time backed by a single kernel level thread. And now each time you switch from one aspect of your calculation to another, you don't have to pay the dispatch cost for switching, right? Because it's all still in user level. And so how you scope your threads, whether they're user level or kernel level, can have a dramatic impact on the ultimate performance of your computation. Okay. Any questions about this? Make sense? So whether it's POSIX or something else, it doesn't really matter. The idea is you can tinker with the mapping of your threads to keep them purely user level or so that they're seen at the kernel level. Okay, so let's lastly take a look at multiprocessor scheduling. So CPU scheduling is, as complex as you might imagine for regular one single CPU. It gets even worse when you're dealing with multiple CPUs because now the decision isn't just what your ready queue is, the prioritization. You're also concerned about which particular core or which CPU this thing executes on. And the reason for that, or some of it, has to do with non-uniform memory access. So suppose you have a multiprocessor system and you want to perform an operation on something that's in memory. Now, of course, some multi-CPU or multiprocessor architectures have memory close by each of those CPU instances. And so the channel or pathway to get from memory to a particular CPU, it's localized. Now, if you use one part of memory, that's local to one CPU. If you use another part of memory, that's local to another CPU. So if you perform a computation that makes use of memory and that memory is not local to that CPU, it'll allow you to do that, but you're going to incur an additional cost in order to get to that memory, right? You're going to have to load it, and you're going to incur a slowdown when you do that. So CPU scheduling is much more complex. There's so-called homogeneous processing within a multiprocessor, and there's also so-called asymmetric. With asymmetric case, only one processor accesses the data structures, whereas with homogeneous, it's all multiple instances of the same thing. So in symmetric multiprocessor, each processor is self-scheduling, right? So all the processes are in a common ready queue, and that scheduling just happens. That's kind of nice. But with this idea of processor affinity, you can designate that a particular process or particular thread is bound to a specific CPU instance. And the reason you want to do that is because all the other resources, like the data resources, are local to that CPU. Now, certainly the system will allow you to migrate data and fetch data across CPUs, but you're going to pay a cost for that, and it's typically with a slowdown because memory is much slower than CPU. So there are so-called soft affinities where it's just a mild suggestion to the system. If you can, make sure that this process is associated with this CPU. And there are hard affinities where it says, okay, well, I'm going to specifically pin this thing so it can only run on that CPU. Okay? And there's all sorts of variations for this. So let's take a look at what NUMA, a non-uniform memory access, what that issue deals with. So in this particular schematic, and this is in the book, this is a typical multiprocessor architecture. So you have a CPU, and it is local with a certain amount of memory, right? So the memory channel is direct to the CPU. And then you have your system bus for your computer connecting together another CPU node instance, right? And so if you're running on the CPU on the left, and you want to access a data structure that's in your local memory, of course, that's going to be very fast. Now, if you want to access some data structure that's in the memory that's local to a different CPU, you're going to have to traverse the system bus, and that has much slower bandwidth than that channel or pathway directly to the CPU. Now, if you look at a lot of modern CPU specs, they'll talk about memory bandwidth and how many channels to memory that it has, and that talks about local memory. But typically in the multiprocessor design, you always have memory local to some CPU. And so this NUMA, or non-uniform memory access, talks about the fact that where you place your algorithm has an impact on its performance. And in some cases, if you place your algorithm that operates on your data structure in a different location from the data structure on which it operates, you're going to have what's called non-uniform memory access. You're going to incur slowdown because you're accessing this thing by traversing the bus instead of natively through these custom channels that speed up memory access to the local CPU. Okay? Any questions about this? So this will come into play. Let's say you work at a hedge fund and you're doing calculations trying to predict which way prices will move for some basket of commodities pertaining to a market. This will come into play for calculations like that, or if you're doing numerical methods, maybe you're trying to multiply large matrices of values and solve some system, or maybe you're trying to simulate something, right? You have a stochastic simulation, maybe for flight arrivals and flight takeoffs, and you're trying to use that to influence the layovers, for example, for an airport. If you have a lot of moving parts with high throughput calculations, this NUMA can really dramatically impact the performance of your computation. And so for a multiprocessor system, for high performance applications, it's not just what your algorithm is doing, it's where it's doing it, right? That's what makes this hard, right? And if you want all these things happening in parallel, where you do it really matters. And you can actually spend an entire semester or two in a graduate program just talking about parallel versions of algorithms. Like how you take data structures and algorithms. There are courses called parallel algorithms, and it takes into consideration about placement and memory access and speed up and what's called overhead due to parallelism. And they also talk about, in algorithms, how you talk about time complexity. In parallel algorithms, you also talk about something called message complexity because you're concerned about the characteristics of getting access to these data structures. Okay? All right, any questions about this? All right, so I do hope you go to grad school. In fact, grad school is a lot easier than undergrad because you're focused on a much narrower set of topics and you're only in your discipline. You're not just taking these other things that you might or might not want to take unless you want to. Okay. All right, so let's look at some of these issues in multiprocessor scheduling. One of the things you're concerned about is load balancing. And what load balancing says, if you have these multiple processors, you want to make sure they're all equally busy. You don't want to have one process doing all of the work while another processor is sitting idle. And so this idea of load balancing is how do you take your ready queue, or all of the units of work admitted to the system, and how do you distribute them so that you keep all parts of your system working, right? And so this load balancing can happen in many different ways. This so-called push migration. So what happens in push migration, you're a processor and you have a ready queue, and this ready queue has a bunch of tasks on it, and you know how much work you have if you have an estimate for the burst times and you know how many things are in your ready queue. So then what you do in between selecting programs for dispatch on your particular CPU, you check the other CPUs and say, how busy are you? How busy are you? And if you find that one is much more lightly loaded than you are, then you go ahead and you take this PCB off your ready queue and submit it to the other ready queue for the other CPU. Okay, easy enough. And then the other is called pull migration. In pull migration, the onus is now on those lightly loaded CPUs, right? If a CPU doesn't have a lot of work, right, it says, okay, well, I don't have a lot of work right now. Let me look around at all the other CPUs on the system. And if I find that another CPU has a large workload ahead or it's very heavily loaded, I'm going to pull one of those tasks from its ready queue and add it to mine so that I increase my work, right? And so this load balancing can be accomplished not just in these two ways, but in a number of different ways. But the whole point behind this load balancing is to keep all parts of your system busy and running, right? To try to even out the workload so that you don't have one CPU 80% loaded to its capacity and the others are only 10% loaded. You want to try to make it as even as possible. Okay, but again, the practical consideration is this doesn't happen for free. If you're going to migrate a process, it's easy enough at our level to say, oh, you just take its PCB and put it on the other ready queue. That takes time, right? And you're going to have to pull data across the system bus in order to do so. Okay. So then there's also multi-core, and multi-core is a trend, maybe the last maybe 10 or so years, instead of having multiple processes, to put those multiple processes on the same physical chip, right? And when you do that, you can have them run at full speed instead of being limited by the bus bandwidth when you're trying to do things across CPU instances. And so this multi-core is a lot faster, right? Which is kind of nice because at the end of the day, the goal is throughput and processing speed. So in multi-core, in this diagram, on the top we have a depiction, and this is in the book, a depiction of what it looks like from the chip's perspective. So we have a single CPU, and this is just one piece of silicon, right? And on that single silicon chip, you have more than one processor implemented. And so each one of these processors in this case is called a core, and we have 4 cores in this case, core 0, core 1, core 2, and core 3. And each one of these cores in this case supports 2 hardware threads natively. So we have a total of 8 hardware threads implemented by 4 cores. And the difference between multi-processor and multi-core is that imagine if we had a separate processor, a separate chip, right? That's multi-processor. But here, we multi-core, we have more than one processor implemented on the same piece of silicon. And when you do that, as I said before, you can get speedups, especially when it comes to things that require more than one CPU. Let's say if your computation is in a different core from your data structure, you don't incur the same costs for non-uniform memory access. And so on the bottom, we have the view of the operating system, right? This is a physical view on the top, and on the bottom in that box is how it looks from the perspective of the operating system. And so from the perspective of the operating system, it looks like we have 8 CPUs. Now you might be asking yourself, why is it 8 and not 4, right? Because I see 4 CPUs. Now remember, a CPU from the operating system's perspective is the ability to execute instructions. And this ability to execute instructions is implemented at the processor level in the silicon as a hardware thread. So each one of these hardware threads is associated with a program counter, with a stack pointer, with a register file, and so forth. So while it's a so-called hardware thread, to the operating system, it looks like a unit of execution. So it almost looks like a CPU and does look like a CPU to the operating system. So from the operating system perspective, for this physical architecture, it looks like it has 8 units of execution, 8 CPUs. And therefore, when you implement these constructs, right, you're choosing 2 things when you're trying to scale up a high-performance system. You're looking at the number of processors, you're looking at the number of cores, you're looking at the number of hardware threads, and then you're also looking at, and a lot of people ignore this, you're looking at the bus bandwidth. Now you'll notice at certain price points, branding aside, you'll notice that some CPUs, when they advertise it, they'll say, oh, it has a 1 terabyte disk drive and it has all this RAM, but they don't tell you what the bus speed is. Now typically the bus speed is measured in megahertz. They'll say like, a 1000 megahertz or 1 gigahertz bus or something like that. You'll notice that the more expensive computers, particularly the server machines, they'll have a much higher bus bandwidth, right? Likewise, you'll notice when you buy or spec out a system, the more cores you have, the more expensive that will be, right? And that's for engineering reasons. And also the more hardware threads you have, the more expensive that system will be, right? Because all of that takes engineering effort and you have to pay for these things. So whenever you spec out a system, it's really important that you that you pay attention to all these parts of the system, including the bus, as well as the number of hardware threads, the number of cores, and so forth. Now, if you're just, using a word processor to type papers and maybe surfing the web and, streaming media, you don't need a 16-core machine with 4 hardware threads per core and all that good stuff. I mean, you're welcome to buy one just for yucks if that's what suits you, if that's what you want to do. But you only want to get as much computation as you need for the types of tasks that you're going to run. Anything else is really just wasted money. Okay. All right. So this is what multi-core, multi-threaded looks like from the system perspective, and this is what it looks like from the operating system. And so I think we're right up at 10:45. I will end there since that's what time is for the class, and we will meet back up on Tuesday, and we will have written exam number 2 on Tuesday. Okay. Any questions? So with that, we'll end there, and I'll see you all on Tuesday.